Okay, welcome back. Today we're going to be looking at we're going to continue looking at working with margin of error and using it to compute a confidence interval for P. And we said we would take our margin of error and use it by adding it and subtracting it to a point estimate for P, which would usually be P hat. And we talked about how to calculate the margin of error yesterday. So today we're going to look at a certain situation where we might have some guidelines with regards to our margin of error, where we have to keep it below a certain size. In other words, we don't want to have a nice wide confidence interval. We want to keep it as narrow as we possibly can. And there are a few ways to do that, but one of the things that we can control more than anything is our sample size. So again, we can control the margin of error by adjusting one of two things. Those things would be either the confidence level or the standard error that affects the margin of error. So the confidence level, we're pretty much going to not want to sacrifice anything because we want to keep our confidence level up. We don't want to drop down our confidence level and have to worry about that. So what we'll typically use is a change in the standard error. Now, standard error is the square root of P hat times Q hat, all divided by N. And we can't really change the P hat and the Q hat. We don't really have much control over those. So since our sample proportion can't be changed, the only part of the standard error that we can adjust is changing our sample size. And you can probably piece together by now through all of our other classes that changes in sample size definitely have an effect on the variation of the sample, or the sample distribution, excuse me. So that's due to the fact that most cases we're dividing out by some factor of that sample size. So as we continue, we're trying to reduce our margin of error to a certain level. And to determine the size of the sample that we're going to need, we're going to solve the following equation, or actually a following inequality. That inequality would be our critical z times the square root of p hat q hat over n is going to be less than or equal to our margin of error. Now, depending on the problem, for our confidence level, z star will be set to that level, and our margin of error, of course, would be what we were trying to stay below. So unless we have some preliminary data to suggest a value for p hat, we're usually going to assume that it is 0.5. Now, we might have done another study with a smaller sample prior to beginning, so we might have an idea of what we want p hat to be, but usually we don't have any idea what p hat or q hat are going to be, so we'll set them to be 0.5. And the reason why is if you play around with the numbers, you'll find that the biggest product that we can get for P hat Q hat is going to come from 0.5 times 0.5. Otherwise, it's going to be steadily decreasing from there if we make changes. So we'll take the most conservative approach we can, which is to assume that P hat is 0.5. And again, that is the safest assumption since it yields the largest standard error that we could get. So we're going to keep that at 0.5. Of course, Q hat would be 0.5 as well. And then we're going to isolate that n and find the n that would give us the best margin of error that we would be able to need. Here's an example we'll look at, kind of help clear some things up. We're doing a study for our sociology class. We want to estimate the number of college students that have at least one tattoo. We must use a 95% confidence interval, and we cannot have a margin of error that is more than 10% or 0.10. So we're trying to find the proportion of students that have at least one tattoo. And we're going to take a sample, we're going to p hat, and work with it. But we know no matter what our p hat is, we want a margin of error that is going to be, I should say no more than, I guess there's a typo there I'll need to fix, but there's no more than 0.10. So in order to keep the margin of error below 0.10, we can only make changes to our sample size like we've said. So we'll solve the following for n given that our margin of error, ME, is going to be 0.10. So here we go. We're going to use p hat then would be 0.5. And again, this is the most conservative estimate since it makes the margin of error larger than any other value. So we'll take this formula and we will plug in everything, p hat and q hat, of course, being 0.5. So that gives us 1.96, which is the critical value for the 95% confidence interval, times the square root of 0.5 times 0.5 all over n, less than or equal to 0.10. And we just solve this inequality. The first thing we do would be one of the first things I would do would be to divide 1.96 over. So we get square root of 0.25, which is just 0.5 times 0.5, over n is less than or equal to 0.05102, which is basically what 0.10 divided by 1.96 is. Carrying it further, we're going to get rid of that radical by squaring both sides, so we get 0.25 over n is less than or equal to 0.002603. And then we would multiply n over, divide back, and our answer is going to be that 96.04 is less than or equal to n. In other words, n has to be bigger than or greater than or equal to 96.04. Well, since n has to be bigger than 96.04, that would basically mean that our sample size must be 97, which is the next largest sample size that we can take that is still bigger than 96.04. Keep in mind, if we went down to 96, our margin of error would be a little bit bigger than 0.10. Although it would be very close, it still would be a little bit bigger. So we're going to have to go over 96.04 and get a sample of 97. Again, this is just a quick example of how you would determine what sample size works best for your needs, depending on some limit that you might have on your margin of error. Hopefully you got a little bit of an idea of how to do that, and you'll have some more examples of this in your assignment. Hopefully you can use that formula or that inequality to solve and figure out what your best sample size would be. Have a nice day.